Welcome back to a bright sunny Saturday in Thailand, where I woke up and my portfolio was really not happy with a giant drop in the Tesla stock price overnight. But I'm here for the long run, so you live by the Elon, you die by the Elon. But today we're going to talk about flash memory, which is the ability to store data in your microprocessor which survives reboots of the whole device. So you can use it to save things like parameters and user input and things that you need to be there every time the device wakes up, but that can change and you don't want to hard code them into your code. So let's dive in. Okay, as with all things Atmel, you have to go into Atmel Start and add the thing that you want to work on next. So what I did is I created a new flash driver from the non-volatile memory control underlying device structure. So we now have something called flash_0, which manages the way I can read and write to that flash memory. And as opposed to something like the USART, there is not a lot of configuration that happens here. You have only one driver, and you can change with the read mode selection, power reduction, and disable the cache, but I'm just going to leave all that by default. So I say generate project, and it generates a bunch of code for me. But the first thing we need to do is look at how memory is actually stored from the view of the microprocessor. Now, popping over to the 1293 page SAM C20 C21 family datasheet, we can see that our chip of choice, the C21E18, has 256 kilobytes of flash and 32 kilobytes of RAM. Now, in the big picture, when you can buy a gigabyte flash memory stick that you can move files around, this doesn't seem like a lot, but for a microcontroller, this is plenty. Now, let's take a look at the memory map of how all the different memory components live in the processor. Now you can see over here, we've got the global memory space from 0 to FFFFFFF hex, which is roughly 4 billion. This is the most amount of space that you can define with a 32-bit number. And you can see that the memory space is carved up into different chunks. And the first chunk from 0 to 20,000 million hex, or whatever that number is considered code, and then that's further broken down into internal flash space and reserved. So this may or may not exist. You're just not allowed to play with anything in the address space here. Now, the internal flash size is going to depend on the chip that you have in your system. You can see the other chunks of address space. This one is static RAM, which is variables which can be very quickly read and written during execution of your program. But this all goes away when the power goes off. Then you've got peripherals, and peripherals and I/O buses. These are actually devices that exist in hardware, but they have memory storage requirements to do their job. And then sometimes even the physical port that reads and writes data goes through what's called a memory mapping facility. So it's kind of a fake memory address. If you read from a particular address in here, you might be reading bytes off the serial port. But now let's just go in and take a deeper look at the structure of the internal flash. And remember, on all chips in this product family, flash starts at 0 and goes to 400,000 hex. This is where everything happens. Okay, so our embedded flash goes from 0 to 400,000 hex. Our device is an 18, so we have 256K. 256K is 40,000 hex. So in reality, the memory space for flash on this chip goes from 0 to 40,000 hex. Now, some of this is reserved. The compiler and the linker and everything that makes and puts our program onto the chip is going to reserve from 0 to the length of the program to actually store the opcodes to make our program work. So we can't start writing from 0 for our flash purposes, otherwise we're scribbling over the top of the program. So we need to find a space somewhere comfortably after however long our program is, but before we hit 40,000 hex. Now, to further complicate things, the layout of flash is not just simply 0 to the end. It's broken up into a number of pages. And in the case of our chip, we have 4,096 pages, and each page is 64 bytes long. Because of the nature of flash memory, you can only write the entire page at a time. I can't just change byte number 7. I've got to rewrite the entire page. And it helps knowing how many pages I have when I'm kind of laying out how I want my information stored in memory. I might want to put different things into different pages. Even though I might waste a little space, it could make more logical sense to my application. And we also need to know this when it comes to the reading and the writing APIs that the framework gives us. One issue with early flash memory was that the technology only allowed a certain number of writes in the same location before it would start failing. That's why early users of thumb drives ended up throwing a lot of them away, because they would have errors. But the good thing is that the user of my board can change all of the parameters, say up to 100 times, and the flash will be good for a minimum of 25 years, but typically over 100 years. They could change the parameters 2,500 times and minimum 20-year retention. So I am not worried in the least about being wasteful in how I write to the data, because I have that luxury. Okay, enough of the manual. Let's look at some code. Now, when I did the generation from Atmel Start, it always gives you this file called driver examples, and it will give you whatever they've written up as example code based on the things that you've configured into your project. So that's pretty cool. Now, sometimes these examples are a bit lacking, and you'll understand in a minute. So the first thing it does is declare two 128-byte arrays. And then it comes into flash 0 example. First, it gets the page size of flash 0, and we know in our chip that that is 64 bytes. Then it scribbles some data into memory from 0 to 64 into this array, and then it does flash write to the flash device of this number, hex 3200, take the data from the source array that it just populated, and the page size is 64. Now this is important because this tells the underlying code that flash write calls that we're dealing with 64-byte pages in our chip. So we go from the abstract concept of a flash device to you need to deal with me in 64-byte chunks, and that's fine. Now, one thing I forgot is there is, as in all other Atmel devices, there's an init routine called flash init, but it's automatically called for us at once in the very first call we make in our program. So we don't have to worry about that. We can go straight into getting our page size, and then we can scribble data into the flash. And even though we can make an array that's much longer than one page, this API will do the chunking of the pages for us and successfully write the flash. Now, let's get back to this 0x3200. I've seen this in a couple of pieces of example code when I did some Google searches. This is the destination in flash memory where you want your information to be stored. Now, why did they pick hex 3200? I have no idea. They didn't explain it. And what if my program is sufficiently large that it's hex 3201 bytes long? That's just the executable part of my program. Using this number, I have just scribbled on top of my program, and that's never good. These microcontrollers and this kind of programming interface is extremely powerful, but extremely dangerous. It's like a gun with no safety and you're waving it around the room. So I need to figure out how long my program is and then put a comfortable amount of blank space after it before I decide to start writing my flash. Now, I've got a very small amount of data that I want to write, and I can write up to 0x40,000. This is the end of my flash memory space. So I could even say 0x30,000, which is clearly going to be more than enough to protect me from the end of my program and have 10,000 hex bytes of storage space. So I'll probably end up doing something like that. Okay, so let's take a look in my code. Most of my effort has been just to find a way to store the user parameters away because the flash requires an array of bytes, and that's all it knows. You put some stuff in an array of bytes and it'll write it to flash. So I've got this array of 64 bytes, and then I set up these other pointer variables to point at the appropriate place in the array so that when I write to this pointer, a number inside the array gets updated. And then I can write that to the flash, and then I can read that back. And the way I set up the array slots is like this. So here we have our array name, and I want to set up my first variable to write in there called first boot, which is just a flag to see if I'm dealing with virgin flash memory or the user has already written some values. So I set up the pointer for first boot to the address of the array's 0th element. So first boot is pointing to that first element out of the 64. Now, for all of the other values, these are also pointers, but they're declared to be pointers to a 32-bit value, which is 4 bytes. And each of my parameters takes up 4 bytes. And that's important. You'll see that in a sec. So as I want to put these variables into slots into the array, I then make them point to the first boot plus 1, plus 2, plus 3, plus 4, 5, 6, and 7. Now, there's a little pointer arithmetic happening here. This is not a value in a variable. Say that the temperature is 29 degrees Celsius and I increment it by 1. I'm actually changing the pointer, changing this pointer variable to point to a memory location represented by the start of the array plus 1. And the plus 1 here is going to move me ahead 4 bytes because this is of type pointer to a 4-byte value. So what I'm doing with plus 1, 2, 3, 4, 5, 6, 7 is I'm going through the user parameters array and setting these at 4-byte intervals. So I've got lots of space. And the good thing is I don't really care how the data is stored in those 4 bytes. Could be big endian, could be little endian. For the floating points, it could be IEEE 758, I think it is. That's all transparent to me. All I need to do is write a variable in and read it back out. I don't care about the byte ordering and bit ordering within that. And it all just magically works. Okay, at startup, I call initialize flash, which uses the get page size API, which we need to do. Then this is where I set up those pointers into the array. Then I read from Flash, and it can't be any simpler. Flash read from the Magic Flash device. At the base address, which you can see I have set to 30,000 hex, here's my array, and the page size is 64. At runtime, that gets filled in. I check for an error. If there's an error, I'll handle that later. Otherwise, I need to detect if this is the first time this board has ever been booted up. And I detect that by looking for a -1 in the first byte. And you can see that right here. This is the flash memory sitting at 30,000, and it's all FF. So FFFFFF is -1. So if I see that, I set some sane parameters, and then I write the flash back out to put a good set of initial parameters into flash. Then I carry on with the rest of the program. Here's where the problem comes in. So let's start this thing up. I've got a breakpoint here. It's going to be the first boot, so let's see what happens. So we have detected that it's first boot. So I'm going to flash the parameters, and you can see here in the array, it's 1, 0, 0, 0, 54, 0, 0, 0, 32, 0, 0. So we should see that reflected in the first row of the flash. And I click go, and nothing. It's still the same. There's a little refresh arrow here. I'm clicking on the refresh, and it's definitely the base flash at address 30,000. My error code comes back 0, which means no error. So I'm just going to continue on like everything was fine, but it doesn't write. So let's continue. We'll come over here, and we'll do a command, mv equals 85. Okay, so now I've updated the parameter from 54 to 55 hex. This is my 85 sitting here, and I'm ready to do another flash write. I click step over. Nothing. It's exactly the same. It's all -1s. Refresh, refresh, refresh. I got no error, but I get to continue on with my life. Now, over here, we can see that the parameter was updated within the RAM part of my program, but it didn't write to flash. Now, let's take a look at why this happened. I did a lot of Google searches about ASF4, Atmel, flash_write, fails, doesn't work, and I finally came across this. Some people in one of the Atmel forums, where the users help each other, this guy said, you can just uncheck the cache all flash memory accept box under project properties tools. When debugging a memory window, the ICE only retrieves data from the memory range currently displayed, which is virtually instantaneous. Let's see what that means. So we're coming over here, project properties, tools, cache all flash memory except. So if I uncheck this, hit save, we debug again, hit go, we come up here, Virgin boot, my parameters are set, 0, 1, and 54. I step over. Look at this. Look at this. 0, 1, 54. These are the values that changed. It wasn't me. It wasn't my code. It was a bloody parameter in the debugger that's telling it to actually reflect the values that I'm changing in the flash. This is what will give a company a bad name. There's no documentation about this. I only found it because I Google searched to the end of the earth. I just want to kick somebody in the dick over this. This is irresponsible of the company to do this. It's bullshit. And as the more I work with this thing, the more frustrated I get at how badly documented things are. It's ridiculous. I even followed through in the source code for this flash write. You'd think if anything goes wrong, you would get an error code. No. All it does is check to make sure I'm passing in non-zero parameters. But when it calls the underlying write to the flash hardware, it doesn't check, nor does it return back up the chain an error code. This is magically ignoring anything that goes wrong to do with flash under the covers. This is unacceptable. This is crap. And I am so mad right now. I can't even believe it. So, I'm going to wrap this up, get all my values reading and writing from flash properly, and go and get a really stiff drink, which I find myself doing more and more with this project. Oh, and just before I go, I want to point out yet another tool-related bullet in foot injury that Atmel is pushing on us. When I first started trying to use my floating point numbers for the calibration, like 1.01 or 0.235, when I printed them out to the terminal, it was just blank, which was weird. So I did some searching and I found that I have to change a setting. And if you go into your project properties, you go to the ARM GNU Linker General Settings section, you uncheck a box that says Use Size Optimized Library. Now, this tool defaults to ignoring the use of any floating point numbers. And I can understand that in a very, 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 very memory constrained system. But to be completely silent about it when I'm using a chip that is got all the capacity I could ever use in the world, and that not make it a part of Atmel Start. That would be good to have a little checkbox there that says, yeah, sure, I want to use floating point, and just don't ignore when I try and use it. So once I uncheck this box, which of course I found with a series of Google searches, all of a sudden my calibration numbers started showing up on the terminal, because the sprintf method in the runtime library ignores the %f directive to print a floating point number, unless you do this. So the tool is working against us. Things that are easy are made far more difficult. They're not in the documentation. I have to do Google searches to find other people who have run into the same problems and then fix them. So Mikey is not a happy boy right now. As you stare out on my beach, I would ask you to subscribe to my channel and click like on this video so YouTube thinks I'm worthy again, and I have so many people on my channel that they'll give me 10 cents a day in ad revenue. So I thank you for that.